All right, let's jump right in. Today we're going to talk about one of the most powerful, most profound ideas in all of science. Seriously, it's this single concept that acts like a kind of universal grammar, and it connects the subatomic world of quarks, the very fabric of space-time, and, get this, even the abstract world of money. I know, it sounds totally impossible, but stick with me, and you'll see the hidden logic that ties it all together.
So, let me start with a puzzle for you. What could a tiny little particle, the geometry of our entire universe, and a unit of currency possibly have in common? It sounds like a trick question, right? But they are all governed by the same deep principle, a principle that shows us how the universe creates order out of what seems like total freedom.
Okay, let's dive into it. The key, the absolute key to unlocking this whole thing is an idea called symmetry. But we're not talking about just, simple mirror images. We've got to understand the difference between a rule that's the same everywhere all at once and a rule that can actually be different from place to place. So first, imagine a world with what's called a global symmetry. It's like a strict law that says every single clock on Earth has to be set to one universal time. It's rigid, it's simple, but it's also a little unnatural, don't you think? Now picture a world with local symmetry. In this world, every city is free to set its own local time. This local freedom feels much more realistic, but it creates a new problem. How do you compare the time between New York and Tokyo if their clocks are all set independently? You need some kind of system to connect them, right? And that's the absolute crucial point. This beautiful idea of local freedom, of rules being independent at every single point in space and time, well, it isn't free. To make it all work, to keep a consistent set of laws across the universe, the system has to pay a price. Something new has to be introduced to stitch everything back together. And that price is what we call a force. The framework that describes all this is called gauge theory. This is the big idea. Forces like electromagnetism aren't just random things that happen to be in our universe. Nope. They are the mathematical consequence, the necessary cost of allowing the laws of physics to have local freedom. In a very real way, forces are the universe's solution for connecting all these independent points. Okay, so if forces are the price of local freedom, what does that actually look like? Let's see how this pretty abstract principle becomes the very bedrock of our physical reality. And this is what's so amazing. 3 of the 4 fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, are perfectly described as gauge theories. They aren't just things that happen, they are things that must exist for the universe to be locally symmetric in the first place. Now, this table shows us something incredible. The kind of freedom you demand dictates the kind of force you get. These codes you see, U1, SU3, they're just mathematical labels for different flavors of local freedom. A really simple freedom, called U1, gives birth to electromagnetism and the photon, but a much more complex freedom, called SU3, gives us the strong force and its 8 gluons. Different rules for freedom literally create different forces. So let's look at that simple U1 freedom. Mathematicians call it commutative, which is a fancy way of saying the order of operations doesn't matter. The consequence of that is actually pretty simple. Its force carrier, the photon, is electrically neutral. And that means photons don't talk to each other. Light just passes right through other light. But for the strong force, the SU3 freedom is non-commutative. The order absolutely matters. It's like putting on your socks before your shoes. And this is a total game changer. It means the force carriers themselves, the gluons, carry their own color charge. So gluons interact with other gluons. This self-interaction is what makes the strong force so incredibly powerful, like a tangled cosmic knot that binds quarks together so tightly inside protons and neutrons. So, gauge theory is obviously an unbelievable tool for physics, but here's where the story takes a wild turn. What happens when this physics tool ends up in the hands of pure mathematicians? Well, something truly unexpected. The physicist C.N. Yang described it perfectly. He called it a miraculous convergence. The very same mathematical language that physicists had cooked up to describe particles, it turned out to be the key to solving a deep mystery about the nature of space itself. So, the mystery was this. What does 4-dimensional space actually look like? And I don't mean 3 dimensions of space plus 1 of time. I mean 4 pure spatial dimensions. For decades, mathematicians struggled to classify all the possible ways a 4D space could even be structured. And the answer they found was just shocking. It turns out that unlike any other dimension, there isn't just one single unique way to structure a 4-dimensional space. No, there are infinitely many exotic versions, spaces that are fundamentally the same, yet somehow
impossibly different.
So how on earth did they figure this out? Well, the physicist's toolkit, gauge theory, was the key. A mathematician named Simon Donaldson realized that the equations describing particles could be used as a kind of probe to study the very structure of 4D space. And by doing that, he proved that 4 dimensions are uniquely bizarre. It's kind of like the Goldilocks dimension. It's just complex enough for these weird structures to exist, but not so complex that they all collapse. Physics had just solved a deep problem in pure math.
All right, now for the most mind-bending leap of all. We've gone from subatomic particles to the geometry of the cosmos. Can this same idea really apply to something so human-made, like the stock market? Some researchers think so, and you know what? The analogy is surprisingly elegant.
So here's the core analogy. Think of the market as a kind of space. Choosing a currency, like the US dollar, that's like choosing a local ruler to measure value. That's your gauge. An exchange rate, well, that's the connection that lets you translate a value from one currency to another. And arbitrage, in this language, that's the mismatch, the curvature you find when you translate value all the way around a loop and you don't end up back where you started.
So, in this geometric language, a risk-free profit opportunity, an arbitrage, is literally a measurement of the curvature of this financial space. If you can trade dollars for euros, then for yen, and back to dollars and somehow make a profit, it means the space of currency values isn't flat. There's a twist in it somewhere.
The theory suggests that the force driving markets is just traders trying to exploit and get rid of these arbitrage opportunities, which is a lot like a physical system trying to flatten its own curvature to settle into its lowest energy state. Now, it's really important to get the critique here. This is a powerful analogy, but it's not physics. In nature, the laws are just given to us. In finance, the rules have to be inferred from messy human behavior, and that makes the connection a lot less certain.
Okay, so let's pull all these threads together. We've gone from the very real forces holding matter together to the super abstract structures of pure mathematics, and even to these speculative models of our own financial systems.
This one core idea, gauge theory, it just radiates outwards. The principle that local freedom requires a connection. I mean, that's the foundation of particle physics. It's the language of gravity. It's the key that unlocked 4D space. And it's a framework for understanding everything from weird quantum materials to financial markets. It's just incredible. So whether we're talking about comparing the quantum phase of an electron at 2 different points, or the color charge of a quark deep inside a proton, or even the value of a dollar versus a euro, at the end of the day, we are asking the exact same fundamental question. How do you connect things that have local independence? And gauge theory gives us the answer. Connection is the price of freedom. The forces that weave our universe together exist for the one precise reason that its individual parts are allowed to be different. And that leaves us with one final, fascinating question to just chew on. If the same deep mathematical grammar can describe both the fundamental reality of the cosmos and the complex, messy systems of human value that we've created, what is that telling us about the nature of structure and connection itself?